we're finally to the last section of chapter 19, which is 19.7, and it talks about the relationship between free energy and equilibrium. We want to figure out what delta G is going to be at conditions that are not necessarily at equilibrium, or not necessarily at standard conditions. So we can calculate delta G under any conditions, at standard conditions, at equilibrium, any of those things, by using this particular formula. So delta G, not necessarily at standard conditions, is equal to delta G at standard conditions plus RT natural log of Q. So delta G with the little circle, that's delta G standard. R is the molar gas constant that you're quite familiar with. We've used that a couple of times. T is our temperature in Kelvin. And Q is our reaction quotient. We saw the reaction quotient back in chapter 15, and we're going to see it again here. But we can get information as we change our conditions, so it's not at standard conditions. We can see how that affects the value of delta G. Now, if we happen to have, so there, Q is the reaction quotient. If we happen to have everything at standard conditions, well, at standard conditions, all of the gases are at 1 atmosphere, and all of the things that are in solution are 1 molar. So at 1 atmosphere, 1 molar, that means that the value of Q at standard conditions is going to be equal to 1. Well, the natural log of 1 is equal to 0. So that means this whole term will drop out to 0. So if we happen to be at standard conditions, then delta G will be equal to delta G at standard conditions, which I know that seems a little bit circular, but that is sort of proof that this equation actually works. So we want to look at number 73. And so here we've got number 73. I've written down that equation that we just had, delta G equals delta G standard plus RT natural log of Q. And then I've also looked up the Gibbs free energy of formation. And the reason that we're going to be able to use Gibbs free energy of formation in doing this calculation is because we're doing it at 298 Kelvin. If we did it at any other temperature, then we would need to calculate delta H, delta S, and then use the formula delta G equals delta H minus T delta S to get our delta G standard. We will see that not in the next problem, but in the problem after that. So you will get to see an example of that coming up. So using the data from Appendix D, Appendix C rather, calculate delta G at 298 Kelvin. So delta G is equal to products minus reactants. So 1 times 98.28 minus 2 times 51.84. So 98.28 minus 2 times 51.84. And you'll see that that gives us the quantity negative 5.4, and we're going to say negative 5.40. All right. Well, that tells us that at that particular set of conditions, at standard conditions, where the partial pressure of NO2 is 1 atmosphere and the partial pressure of N2O4 is 1 atmosphere, that this reaction will be spontaneous in the forward direction because our delta G is negative. So now we want to calculate the value of delta G when we change the pressures. Well, we're going to need to write out an equilibrium constant, so KEQ. When we're doing this, if we have anything that is in the gas phase, then we're going to write that as a partial pressure. If we have anything that is in solution, like if we had something that was aqueous, then we would write that as a concentration. So it is possible to have mixed concentrations and partial pressures in this quantity. This one, because both of these are gases, are simply going to be partial pressures. We'll have the partial pressure of N2O4 divided by the partial pressure of NO2 squared. All right, and so that is the KEQ. Q is going to have that same expression, but not necessarily at equilibrium. So now we want to calculate what delta G is going to be under these new conditions. So there is our formula for the delta G. So delta G is equal to delta G standard, so minus 5.40 kilojoules plus R is 8.314 joules per mole Kelvin. And I'm writing the units because we need to do a conversion here before we write that natural log. Our temperature is 298 Kelvin, and I'm going to write 1 kilojoule over 1,000 joules. And then finally, we'll do the natural log of Q. Q in this case is going to be the partial pressure of N2O4, so 1.60, divided by the partial pressure of NO2 squared, so 0.40 squared. So that is a 0.40 squared. I am going to fix that so it looks a little bit better here. So 0.40 squared. That looks marginally better. All right, so that is a square quantity right there. I think I'm just making it worse. Anyway, that's 1.6 over 0.4 squared. So we want to evaluate this. I'm going to evaluate this here, the 8.314 times 298 divided by 1,000 times that natural log. So we'll do 8.314 times 298 divided by 1,000. And then we're going to multiply that by the natural log of 1.6 divided by 0.4 squared. All right, and then you'll see that the number we get there for this whole quantity comes out to 5.70 kilojoules. All right, so we had negative 5.40 kilojoules and then positive 5.70 kilojoules, and that's going to give us the quantity of 0.30 kilojoules. So we will see that that gives us a positive value for delta G. So under this set of conditions, the reaction won't be spontaneous in the forward direction, and in fact will be spontaneous in the reverse direction. And it'll continue to do so until it gets to equilibrium, where Q will be equal to K, and the delta G will end up being 0 once we get to equilibrium. So now we're going to go back to the presentation. We've got one more page on that presentation. So I'm going to go back. And we want to look at the relationship between delta G and the equilibrium constant K. So delta G standard and the equilibrium constant K. So here we go. So this is our formula that we were just looking at. Delta G is delta G standard plus RT natural log of Q. Well, at equilibrium, we know this from several slides back, that delta G is going to be equal to 0 and Q is going to be equal to K. So we can substitute these values into that expression, and when we do, we get this. So 0 is equal to delta G standard plus RT natural log of KEQ. We can solve this either for delta G standard, or we can solve it for the equilibrium constant, and I'm going to solve it for both, so we have both equations. So when we rearrange this one, we'll get delta G standard is equal to negative RT natural log of the equilibrium constant K. And if we want to solve that for K, then we just take this, divide both sides by negative RT, and then take the anti-log. And since this is the log base E, we will need to do the anti-log in this fashion. And so we are now going to do number 75 and 78. So I've written down the equation delta G equals negative RT natural log of Q and KEQ rather, and KEQ is equal to E to the negative delta G standard over RT. And so we might be interested in either one of those. In this particular reaction, we're trying to determine the equilibrium constant K. For both of these, we're trying to find the equilibrium constant K, and it happens to be at 298. Since it happens to be at 298, that means that we can use delta G of formation to do this. So we don't have to calculate our values for delta H and delta S, and then plug that into the equation to get delta G because it happens to be at 298. On the next problem, we're going to have to calculate delta H and delta S. It takes a little bit more work, but not a big deal. So I know for this one, this happens to be 0. I can do that without looking that up. But iodine is not 0. And the reason I know it's not 0 is that iodine is not a gas at standard conditions. Iodine is a solid. So since iodine is normally a solid, then we'll have to look up that value. And when we do look up that value, so I'm going to go back over here and here we go. So iodine, I2 gas, is right there at 19.37. So I'm going to write down that number, 19.37. And then HI is also right there, and it is 1.30 kilojoules per mole. And that number is going to be useful in helping us to solve for delta G. And with delta G, we can get the equilibrium constant K. Okay, so now what we want to do is we want to calculate our value of delta G. So delta G standard is going to be equal to products minus reactants. So we'll get 2 times 1.30 minus 1 times 0 plus 1 times 19.37. That's a 19.37. All right. Clear all that. So we'll get 2 times 1.3, and then we'll subtract 19.37. And that gives us a value of negative 16.77. We've got hundreds place, so that'll work fine. So negative 16.77 kilojoules. Now, it turns out R, because we're going to put this into the equation, R is in joules per mole Kelvin, and this is in kilojoules. So we're going to go ahead and convert this into joules. So I'm going to write that as negative 16,770 joules. And then that makes it so that when we plug this into our formula, the math works a lot easier. So KEQ is equal to E to the negative, and then delta G standard is negative 16,770. The wrong number there. So 770 all right, so and that is in joules over 8.314 joules per mole Kelvin, and then our temperature here is 298 Kelvin. So we've got a negative of a negative, so this whole thing here is going to end up being positive, so I'm going to evaluate that thing that is in the exponent. So negative 16.77 times 1,000 and that gave us the, here, I'm just going to do negative 16,770. Okay, so we've got that quantity. We're going to multiply that by -1. All right, so now it's positive. So now let's divide that by 8.314. And then we'll also divide it by 298 Kelvin. And I'm just going to write down that number. So KEQ is equal to E to the positive 6.769, we'll call it. So 6.769. So now when we take, when we use that number, and I'm just going to use the number that's in the calculator. So I'm going to do second E, and then just grab that answer. We're going to get 870. So KEQ is equal to 870. That tells us that this reaction is product favored. So that reaction is product favored. So let's do the same calculation here for this particular reaction. Again, I'm going to save you the trouble of looking these up. I am just going to write down the values that I found in the appendix. So here I've got -168.5. This one is 68.11. The H2O gas is -228.57. And those are all in kilojoules per mole. So first things first, we want to calculate delta G. So products minus reactants. So delta G is equal to 1 times 68.11 plus 1 times -228.57 minus reactants. So 1 times -168.5. So 68.11 plus -228.57. All right, that's this part. And then we want to subtract negative, so minus -168.5. And that gives us the number 8.04 kilojoules. Now, let me look at sig figs here. Tenths place, or so hundredths place, tenths place. So we're going to round that to 8.0 kilojoules. We're going to round that to 8.0 kilojoules. I don't know that it will actually change your answer if you have 8.04 versus 8.0, but we're going to stick with the correct number of sig figs here and call that 8.0 kilojoules. That is also equal to 8,000 joules, because we're going to need to convert it in our equation, because R is in joules. So now let's put that into our formula. So I'm just going to write it down here. So KEQ is equal to E to the negative, and then up on top for our delta G, I'm going to bring this over. Our delta G is 8,000, so 8,000 joules. And then 8.314 joules per mole Kelvin, and 298 Kelvin. So we've got, this will be a negative quantity up here. So I'm going to clear all that, bring my calculator back over, and we'll do, I'll just go ahead and put the negative. So negative 8,000. Divided by 8.314, and we'll also divide that by 298. And that's going to give us E to the negative 3.229. So negative 3.229. And now, in order to calculate the equilibrium constant, we'll just do that calculation. So I'm going to do second E to the X, and that's a negative number, and so we're just going to grab that answer. and put it in there. And you'll see that that comes out to a 3.96 times 10 to the negative 2. We should probably round that to 2 sig figs. I'm going to go ahead and do that and call that 4.0 times 10 to the negative 2. And so you'll see that in this case, our equilibrium constant, KEQ, is a number less than 1. And on this one, our equilibrium constant was a number greater than 1. So you can predict whether the equilibrium constant will be greater than 1 or less than 1. It'll be greater than 1 if delta G is negative, and it'll be less than 1 if delta G is positive. Okay, so here we've got this particular reaction, and right, so we've got this particular reaction, and I am going to do the magic trick again, where I get the delta H and the standard molar enthalpies, and I'm going to put these in here while the video is paused. Hold on. So here we go. Here's the magic trick. All right. Yes, when it comes to magic, I should not quit my day job. I am not much of a magician, but there we go. We have now got the values for the delta H of formations and the standard molar entropies. And the reason that we need those is that we're trying to find the equilibrium pressure of carbon dioxide, and that is essentially going to be the equilibrium constant. I'll show you why that's true in a minute, but you'll notice that it's not going to be at 298 Kelvin. It's going to be at 120 degrees Celsius and 480 degrees Celsius. So our equilibrium constant, KEQ, we'll do products over reactants. When we look here, we've got lead oxide. It's a solid, so it doesn't go in the expression. Carbon dioxide, it's a gas, so we're going to write it as a partial pressure of CO2. And then lead carbonate, it's a solid, so it doesn't go in the expression. So that means that our equilibrium constant equals the partial pressure of carbon dioxide in atmospheres. So once we find KEQ, that means we have already found the partial pressure of the CO2 in atmospheres. So the first thing we'll need to do is to calculate delta H and delta S. So this is, again, products minus reactants, so you should be getting familiar with this. So I'm going to turn off my mic while I do these calculations. Okay, well now that I have calculated delta H and delta S, we're ready to take those and use them in the equation delta G is equal to delta H minus T delta S. Now, just as a reminder, our T needs to be in Kelvin, and so we'll need to convert these temperatures into Kelvin. So for part A, T is equal to 120 degrees Celsius. So we'll do 120 plus 273, and that gives us 393 Kelvin. All right, so our delta G is equal to 88.3 kilojoules minus 393 Kelvin, and our delta S was 151.3 joules per Kelvin, and we'll need to do that extra conversion, 1 kilojoule over 1,000 joules. All right, so 88.3 minus 393 times 151.3, and then divided by 1,000. And you'll see the number that we get there, 10th place, so we're going to call that 28.8 kilojoules. So that is a positive quantity, so delta G is positive. That means at this temperature, this reaction is not spontaneous in the forward direction. So at this particular temperature, this reaction is not spontaneous in the forward direction. Let's figure out what the equilibrium constant is going to be, though. So I'm going to rewrite that as 28,800 joules. And so now when we do our equilibrium constant, KEQ, it's e to the negative 28,800 joules over 8.314 joules per mole Kelvin times, and don't just throw 298 in here, it's 393. All right, so 393 Kelvin. Then we'll do 28,800 divided by 8.314, and then also divided by 393. And that gives us 8.814, and it's negative, so that will be KEQ is equal to e to the negative 8.814. Well, now let's make that negative of our answer. All right, and we're going to do the inverse log, so e to the negative 8.814. So our answer, and that gives us we're only going to do two sig figs here. It gives us 1.5 times 10 to the negative 4. So 1.5 times 10 to the negative 4. All right, since KEQ, we're going to go back up here. Since KEQ is equal to the partial pressure of carbon dioxide, that means that our partial pressure of carbon dioxide is 1.5 times 10 to the negative 4 atmospheres. And that is our answer for part A at a temperature of 120. So now let's do part B. And in part B, our temperature is equal to 480 degrees Celsius. Well, we're going to take that 480 degrees Celsius and add that to 273. So 480 plus 273, and that gives us 753 Kelvin. Quite toasty. So quite toasty. Probably don't want to hang out anywhere where it's that warm. So let's do our calculation. Delta G is equal to the delta H, which is still 88.3 kilojoules, minus T delta S. So there is our T. Our T here is 753. 753 Kelvin. Our delta S is still 151.3, so 151.3 joules per Kelvin. And we'll do 1 kilojoule over 1,000 joules, and that will get these two things into the same units. So 88.3 minus 753 times 151.3 and divided by 1,000. And you'll see the number that we get there. Make sure I've got the same number here. Yeah, so negative 25.6 kilojoules. So negative 25.6 kilojoules. And that is our delta G quantity. Now that we've got that, I'm going to go ahead and write that as joules as well. So negative 25,600 joules. So our KEQ is equal to E to the negative 25,600 joules over 8.314 joules per mole Kelvin. And our temperature is 753 Kelvin. Most common mistake on this type of problem is forgetting to put the temperature. We're so used to putting 298 that sometimes people will forget that. Okay, so I've got negative of a negative, so I'm just going to call that 25,600 divided by 8.314. And then we'll also divide that by 753 Kelvin. And that gives us 4.089. So that equals E to the positive 4.089. All right, well, we can take that quantity. We can just punch that into our calculation. So we'll do E. And I'll just grab the answer rather than punching it in again. And that gives us 59.69. We're going to call that just 60. So we'll call that 60 as our value. So 60. So with that being 60, or here we could write that as 6.0 times 10 to the 1 if we want to be a little bit pedantic about it. So with that, since the KEQ is equal to the pressure, that means that our partial pressure of CO2 is equal to 60 atmospheres. And that is how we do the calculation when we've got a different temperature. All right. Well, I'm going to show you guys one other quick thing here. So here is our presentation, and I click on that, and that is the end of the presentation. So that is the end of Chapter 19. That also means that is the end of the content for the 4th exam.